Hello friends, I am Jyotirvid Pavan Kumar. Welcome to my workbench. Today in this video, I am going to describe a simple, interesting project which is to build a small, handy LED light, portable LED light, and I am going to use this glass jar. This is an empty glass jar to house the complete circuit as well as the LEDs. And this cutting I have made in order to fit the on-off switch. You can do that using a craft knife, but be careful while using knife. So this will be just a portable and handy LED light, very bright LED light. And the beauty of the project is that 6 very intense bright LEDs will be lit using just one pencil cell, 1.5 volt dry battery cell. And I have already made a couple of videos using the circuit which I am going to use in this project, and the circuit is blocking oscillator built around an NPN switching transistor. In my earlier videos, I have described how to use components from a discarded CFL, but if you do not have a discarded CFL lying with you, then you can purchase the components from market. So first of all, let us see what the circuit is. Now the circuit of the blocking oscillator which I am going to use for this project is like this. This is NPN transistor, and I am going to use BC547, or you can use a transistor which you can remove from a discarded CFL. And these transistors come in low power CFLs. You will find a transistor like this in TO92 package, and in slightly higher wattage CFLs you will find transistors which come in this package, which is TO126. So you can use either, but for this project I am going to use BC547, which is a general purpose switching transistor, NPN transistor. We will require a flyback transformer which we will build. So these are the two windings of L1 and L2 of the flyback transformer, which we are going to make on a toroidal ferrite core. And in my earlier videos I have described in detail how to make that. Now one end of L1 will be connected through 1 kilo ohm resistor, 1K resistor, carbon resistor, and you require quarter watt carbon resistor. It will go to the base of the transistor in order to bias the transistor, and one end of L2 will be connected to the collector of the transistor, and this will also be our output. One end of each coil is joined together and it is connected through an on-off switch to the positive terminal of 1.5 volt dry cell battery. This is the positive, and the negative terminal of the battery cell is connected to the emitter of the transistor as well as to the LEDs. So in this project I am going to use 6 LEDs. I am going to use this strip of LEDs, strip of 3 LEDs. You can purchase this strip. These come in two forms. One is a flexible one, but this is not flexible, this is firm with an aluminium background. And I have 3 LEDs in a row. All these 3 LEDs are connected in parallel. But for this project I am going to use two of such 3 LED strips. I place these together and combine them, join them with a solder wire. The plus terminal of one strip to the plus of the other, and negative of one strip to the negative of the other, so that all the 6 LEDs are in parallel. So all the 6 LEDs will be connected here. The anodes of all the LEDs are connected to the collector of the transistor, which also goes to one end of L2, and the cathodes of all the LEDs, 6 LEDs, are connected to the negative terminal of the battery as well as to the emitter of the NPN transistor. Now the reason why I am connecting in this circuit all the 6 LEDs in parallel, the reason being that in this blocking oscillator circuit we will get about approximately 4 to 5 volt at the output, at the collector, spikes of 4 to 5 volt. And as you probably know, each LED needs at least 3 volts across it in order to light up. So if I connect more than one LED in series, then I require a greater voltage here. So keeping this point in mind, I have connected all the LEDs in parallel so that all the LEDs get equal voltage. So this is the circuit diagram. Other important thing is, which I have already explained in my earlier videos, I'm showing red dot at one end of L1 and red dot at the other end of L2. This means how to phase, how to connect both the coils. So that I will explain you when I describe how to make the toroidal, this flyback transformer. This is phasing required so that we get positive feedback in order to make this oscillate. So this is the circuit diagram, and now let us describe the project. Here are all the components, and I'm using BC547 transistor here. Now since the components are very small, in my earlier video I described that I made this jig using crocodile clips, and you can hold a small component like this transistor like this here, and then you can solder, otherwise it is difficult to hold. Another important thing is, for all the electronic components and wires, you must scrape a little bit before soldering using knife or sandpaper so that it easily gets soldered. If you are using transistors from discarded CFL, then I have already explained in other video the lead outs, and the lead outs for this type of transistor, which is numbered D4204D, the lead outs, if you keep the metallic side underneath and the other side, plain side, upward, the side on which the part number is also written. Then the lead outs for this type of transistor is base, collector, emitter. And for this TO92 package transistor, which I removed from discarded CFL, and the number could be 13001 or 13002, number could be different, but it has to be NPN transistor. And for this part number transistor, the lead outs are base, collector, emitter when you keep the flat portion of the transistor towards you. For BC547 transistor, which I am going to use in this project, see, one side is round and the other side on which the part number is written is flat. So if you keep the flat side upward towards you, then the lead outs for transistor BC547 are collector, base, emitter. These are different from the transistor I removed from the CFL. So you have to be careful while making the joints as per the circuit. The lead outs for 547 are collector, base, emitter when you keep the flat portion of the transistor upward. Now for making the flyback transistor L1 and L2, you require a enameled copper wire, about 44 centimeter of wire, like this. This is a smaller piece just to show you. Enameled copper wire. This enameled copper wire is copper underneath, but it is insulated on top. So you need about 44 centimeter length of 30 SWG or 20 SWG, because if you use a thicker wire, since the core is very small, you won't be able to make about 10 turns on this. So use 30 SWG, and after taking about 44 centimeter wire, you fold it in the middle. This is just to show you. Fold it in the middle and don't cut this end. We will do it afterwards. Then this is the toroidal ferrite core, which I have removed from a discarded CFL. You can purchase this from electronic component shops, and take this one end which is not cut, keep about 2 centimeters for joints, and then very carefully you make the turns, but keep all the turns very tight. Pull the wire so that the turns are very tight. So like this you go on winding, and with the length which I have mentioned, you will be able to make 9 or 10 turns like this. I have already made a toroidal coil with 10 turns. Now after winding, then you can cut the other end which was just folded. And for making the joints, you scrape the wire endings with a knife carefully or with sandpaper, and then you tin the wires using soldering iron. You can tin the ends. I have already tinned these ends, otherwise you won't be able to solder them. Tin all the 4 ends. Now that point which I mentioned with the red dot, that means we are connecting together one ending from the beginning of one coil and one ending from the end portion of the other coil. See, this is the beginning side. These are 2 separate coils, L1, L2, beginning, and this is the ending. Now you may not know after cutting the wire which wire is which. So in order to find out, keep the beginning portion separate from the ending, and now find out which wire is which. For that you will need a multimeter, and set the multimeter to continuity testing point, continuity testing, which simply means when you put the meter on continuity testing, if you connect both the probes of the meter together, you will hear a beeping sound. This shows the wire is the same continuity. There is continuity. So I'll touch probe of the meter on one from the ending side and touch each coil from the beginning side. So this is giving continuity. That means this coil is 1 and the other coil is the second. It could be L1 or L2, but it is separate. This is showing continuity. So separate the this is L1, this is L2, beginning side, ending side. Now in order to join together, you take one end of one coil from the beginning side and one end of the second coil from the ending side and join these together. Twist them a little bit and then you can hold in the crocodile and solder the two endings together. I have already tamed the other endings. So this I have explained how to connect both the strips of 3 LED each together, plus on one strip to the plus of the other strip, and negative of one strip to the negative of the other strip with this wire, and then take a red wire from the plus terminal for connection to the collector of the transistor, and a black wire from the negative terminal of the strip to the emitter of the transistor. From the emitter of the transistor, I have connected another wire which will go to the negative of the dry cell battery. And at the base, this is the base terminal, I have connected a 1 kilo ohm resistor. This is 1 kilo ohm resistor, and you scrape the endings, the terminals, and then you can cut because you need a smaller lead. Connect, solder. You can hold the transistor in the crocodile for soldering and then solder the resistor. And now take this toroidal coil and connect one end of L1, like here, one end of L1 which is free, the other side is connected to L2, so the free end of L1 will be connected to 1 kilo ohm resistor. So we will solder it here. And L2, the free end of L2 will be connected to collector of the transistor. Now this is the point where both the coils are connected together. This will go to the switch, on off switch, and from the switch it will go to the plus of the battery. Now in this project I am using this switch. This is a small push fit type of on off switch, push fit. So you don't require any screws to fix the switch on the panel. For this I have already cut a portion as per the size of the switch, and I have connected wires on the terminals of the switch. This wire will go to the go to the common point of L1, L2, and the other wire, which is this one, longer one, will go to the plus terminal of the battery. Now, while connecting soldering onto the terminals of the switch, you must keep in mind that these switches are very delicate, and so first of all you scrape the endings before soldering using a knife or sandpaper so that it catches easily the solder, and do not keep the soldering iron tip for too long, otherwise the switch will be damaged. So I have already tinned and connected the wires. So what we will do is we will place this switch on this cutting and press it downward. So it is a push fit type. So switch is already fitted. Now we will solder this common point of L1 L2 to this red wire which is coming from the switch, and the other will go to the positive of the battery. Now we do not get any holder in the market for holding single pencil cell. So what I have devised is I've just soldered a iron washer, small washer, onto the wire, and I have another washer here. I can hold it in the crocodile and solder the red wire also, which will go to the positive of the cell. If you have any other idea of connecting the battery cell, you can use that and let me know also, because I am also interested if there is a better way of connecting the battery cell. Now, in order to hold the terminals onto the battery, I'll be using this insulating electrical tape, a piece of insulating electrical tape. So let me cut a few pieces. So I'll place, this is the negative side of the battery cell, this is the positive. So I will place the cell here and put a piece of insulating tape so that this terminal is held firmly on the cell. Similarly, I think it is not connected properly, so I will do it again. And this is a bit tricky, but we can't help, there is no other way. So now both the ends of the terminals are connected, and this is working. And I think I will use a longer piece of tape so that the terminals are held firmly onto the cell. and you can switch on and the LEDs are glowing. All the 6 LEDs very bright. You may not be able to see how bright they are, because I am already using quite a lot of light for making this video, but otherwise these 6 LEDs, they are very bright, high intensity LEDs. And the beauty of the circuit is all these 6 LEDs at full brightness are glowing using just one single 1.5 volt dry cell. So now, since everything is ready, we can put it inside the jar. And before doing that, I think it will be good idea to put a piece of insulating tape on the center terminal of the transistor where the resistor is connected, so that it doesn't touch the other terminals. So keeping this in mind, so that all the terminals, they stay separate, you can place everything inside this jar and put on the lid. So this is a handy, very bright LED. This will glow very brightly in a dark room. So this is handy, you can take it anywhere. This is so light and working from just one pencil cell. That's the beauty. You can use a glass jar like this I am using, or you can use a plastic jar also. You may have different ideas for enclosing this light, but this will be quite useful. Now, if you are a student, if you are interested, let me explain a little bit about the core. See, this ferrite core, why we are using ferrite core, why not iron core? Normally the transformers which are run at 50 Hertz AC mains for stepping down or stepping up the voltages, they use iron cores. Now iron cores work better at low frequencies, but at higher frequencies, like in this circuit, blocking oscillator, frequency could be about 40 kilohertz. So iron core won't work. Why? The reason being magnetic permeability. Magnetic permeability of the core is very important. Now, what does it mean? See, this L1, when current is passing through L1, then there is a magnetic field around the coil, right? Whenever current flows through a coil, around the coil there is a magnetic field. Now that magnetic field must be passed on to the magnetic effect of the core, and the better it is done, higher the magnetic permeability of the core. So at this higher frequency, the magnetic permeability of ferrite is much better than the iron core. So iron core won't work at this frequency. It won't give you a efficient flyback transformer, and that magnetic flux, which will be changing as per the field, electric field around L1, has to be passed on to the L2 coil. So if the magnetic permeability is high, then all the changes in the L1 coil will be faithfully transferred to the L2 coil. So the transformer will be very efficient. Also, there is a factor called eddy currents. So eddy currents in ferrite core are low as compared to the eddy currents in iron core. at this frequency the eddy currents, because the conductivity, the electrical conductivity of the core is low as compared to iron, so eddy current losses are not there. So this is the reason why we are using ferrite core. I hope you like this video, and let me know your comments, and I will try to present more and more interesting projects to you. Thank you for watching.